Welcome back to Beyond the Comfort Zone Talking Shit with KING-KAMBUF. Today we're not just looking at architecture, we are really analyzing architectural intelligence at its absolute cutting edge.
Yeah, that's a good way to put it.
So if you're gearing up for a major project, or you need to catch up on the absolute state of the art, or you're just deeply curious about the forces that truly shape our built environment, this deep dive is specifically for you.
That's right. Because we're dissecting an extremely rare and highly specialized set of source material. This is the Architectural Insights with KING-KAMBUF Daily Interdisciplinary Mentorship Brief from December 2, 2025.
And this isn't just like generalized industry chatter, is it?
Not at all. This brief is a synthesis of doctoral level thinking. I mean, it's designed for a practitioner who has to excel as an architect, an engineer, a planner, and a builder all at the same time.
Wow.
It's an immediate shortcut right into the mindset of global leadership in what we call the AEC sector.
Architecture, engineering, and construction.
Hey.
So our mission today is to unpack this intelligence digest and really pull out the critical aha moments. We're going beneath the cladding, beneath the structure, to understand how most advanced design is driven by forces you literally cannot see. Things like thermal stress, vapor pressure gradients, microtorsion, and deep material chemistry.
And the scope of the brief really confirms that the modern architectural leader has to be fundamentally interdisciplinary. There's no other way. We're seeing structural engineering married to civic governance.
Right.
Environmental science merged with high-stakes policy planning and construction physics, right down to the molecular level.
Absolutely. So we're essentially going to map the intellectual terrain of global AEC intelligence. We've got three massive themes to explore today. First, how architecture is evolving into this active climate-responsive infrastructure.
A really big shift.
Huge. Second, the radical new role of the designer as a kind of spatial diplomat, mediating these really complex political and resource conflicts.
Yes, that's a fascinating part of it.
And finally, we're going to drill down. We're going to get into the microforces, the specific high-stakes physics of what's called serviceability that differentiate a structure that merely stands up from one that performs masterfully for decades.
That's where the real genius is.
Let's start with the industry pulse, because the shift here is, it feels tectonic. We're seeing a fundamental rejection of buildings as just static envelopes, right?
Completely.
Cities are now demanding that buildings, streets, public spaces, that they all act as integrated environmental regulators. The structure itself is a climate tool.
The clearest illustration of this has to be what's happening in coastal cities. Places facing immediate threats from sea level rise and increased storm intensity.
Yeah.
The source details this concept of hydro-acoustic breakwater buildings.
Okay.
They're being studied right now in really vulnerable metros like Manila, Rotterdam, and Alexandria.
The name itself,
Yeah.
hydro-acoustic, it suggests a dual function. You're managing water, obviously, but also sound. How does a building become a piece of coastal defense?
It's incredibly sophisticated hydrodynamic engineering. The core concept involves designing the building's submerged podium, so that's the foundation layer below the high tide line, to incorporate these complex, tuned chambers.
Tuned chambers, so like a musical instrument.
Sort of. It's a similar principle. These chambers are basically precisely calibrated voids that function as highly efficient wave dampeners. As a storm wave impacts the structure instead of hitting a rigid wall that just reflects all that energy.
Right, which can cause its own problems, like stour.
Exactly. Instead, the water is channeled into these chambers.
And then what happens inside? Does it just slosh around?
Well, this is the tuned part. The geometry of the chamber is specifically calibrated to the expected dominant frequencies of the local wave energy. As the wave enters, the water flows create massive internal turbulence. You get these destructive interference patterns against the chamber walls and even back into the incoming water flow.
So it's fighting itself.
Precisely. This internal action causes a rapid dissipation of the wave's kinetic energy before it can fully strike the shore or the districts behind it. And it's specific, Manila's dealing with typhoon frequencies, so their chambers would be tuned differently than Rotterdam's, which faces these long-period North Sea surge patterns.
That distinction is key. They're not just walls. They are frequency-specific energy sinks. But the source highlights a major engineering challenge here, beyond just stopping the wave.
Yeah.
If you're dissipating that much raw kinetic energy, you must be creating a huge amount of internal turbulence, pressure shifts, and noise.
Massive amounts. And that's the crux of it. The critical challenge is what the brief calls the foundation-to-chamber interface.
Okay.
You have to design that interface to effectively shed all that hydrodynamic energy without transmitting the residual vibration and that low-frequency acoustic noise into the occupied floors above.
Wait, are you saying the building could act like a giant wave drum?
That's a perfect analogy, exactly. If the acoustic isolation isn't perfect, the occupants on the 10th or 15th floor would constantly feel or hear this deep thrumming, a vibration, every time a major wave hits.
That would be unlivable.
It would completely compromise the program. And this is where that multidisciplinary mandate kicks in. The civil engineer has to ensure structural survival against the lateral loads, obviously, but the architect and the acoustic engineer have to simultaneously guarantee serviceability.
So what does that interface look like in practice?
It has to be a complex material solution. We're likely talking about a combination of heavily reinforced marine concrete with internal layers of, say, elastomeric isolators or specialized mass dampers, something to physically break the vibration path while still maintaining the structure's monolithic integrity against the constant force of the ocean.
So a failure to isolate that vibration, that sound, compromises the entire architectural purpose.
Completely. It's a perfect illustration of how structural survival and human comfort are now intrinsically linked by the same invisible force, in this case, hydroacoustics.
Amazing. Okay, so shifting from the dynamic forces of the sea to the radiant forces of the sun, we're looking at similar integrated thinking, but this time in high-altitude metros. The source details the piloting of high-altitude solar reflective paving.
Right, in cities like Mexico City, Quito, Kathmandu.
And we know at high altitudes, the air is thinner, which means less atmospheric. What's the word? Attenuation.
Attenuation, yeah. Less filtering of the shortwave radiation, the solar energy that causes heating. So these cities suffer from intense urban heat island effects, even though they're high up.
So the response is to turn the street network itself into a climate moderator.
That's it. The mechanism involves a multi-layer paving system that incorporates specific reflective mineral admixtures. These are materials like specialized grades of titanium dioxide or, light-colored, highly reflective aggregate materials, and they're integrated right into the top asphalt or concrete layers.
So instead of absorbing the sun's energy and radiating it back out as heat, which is what a typical black asphalt street does, these pavements are actively deflecting the energy.
Correct. They're increasing the albedo, the reflectivity of this massive urban surface area. The goal is to maximize the deflection of that shortwave radiation back into the atmosphere, which in turn actively regulates the ground plane temperature.
We're talking about reducing ambient temperatures by several degrees across entire districts.
That's the ambition.
Yeah.
Using the streets as gigantic thermal mirrors.
It sounds incredibly elegant, but there has to be a trade-off, right? If you maximize reflectivity, don't you sacrifice surface friction? You'd have slick roads.
That is the core engineering challenge. You've hit it exactly. It's defining a specific paving mix design that successfully maximizes reflectivity without compromising the required skid resistance for cars and even for pedestrians.
Because a high albedo surface that becomes dangerously slippery when it rains would be a catastrophic failure.
Absolutely. So the material scientists have to balance the highly polished, light-scattering characteristics of the mineral additives with the frictional texture required for safety. This means optimizing particle size, the shape, the distribution of the reflective aggregates to ensure they're effective, but they don't create a smooth, low-friction plane.
It's a materials paradox, really.
Mm-hmm.
Safety and thermal efficiency held in perfect quantifiable tension.
Mm-hmm.
Okay, let's look at a couple of other fascinating examples of integrating performance into civic structures. First up, civic fiber mesh roofs.
We're seeing these in Nairobi and Istanbul. They're deploying these large tensioned fiber mesh roofs over public assembly spaces, marketplaces, transit interchanges, things like that.
And the genius here, as I understand it, is that the mesh isn't just a shading device.
Not at all. It integrates optical fibers that can capture diffused daylight and then efficiently pipe that natural light down deep into the space below.
So it's basically a gigantic, soft-touch solar collector for light. You could achieve zero electrical demand for lighting during a day.
That's the goal, a perfect energy offset.
But mechanically, maintaining the integrity of such a vast, thin, tensioned membrane under varying conditions must be a nightmare.
It's a massive structural challenge, and it centers on the mesh-to-column connection. For the mesh to function, both structurally resisting wind uplift and optically, so maintaining the precise geometry for light capture, It needs this critical, constant pretension.
And the problem is thermal expansion.
It's always thermal expansion.
Ah.
In a place like Nairobi or Istanbul, you have significant diurnal temperature swings. The steel columns, the supporting cables, the fiber mesh itself, they all have different coefficients of thermal expansion.
So as the day heats up, everything expands, but at different rates.
Exactly. And this differential movement constantly tries to loosen that critical pretension. If the tension drops even slightly, the mesh can start to flutter, the optical fibers lose their alignment, and the system fails to capture light efficiently.
So how do you solve that?
The connections have to be designed as active structural joints, maybe incorporating hydraulic tensioners or spring-loaded mechanisms that can dynamically adjust to thermal load changes. The point is to ensure the mesh stays perfectly taut and geometrically precise no matter what the temperature is.
So it's a structural system designed to be constantly changing, but always maintaining a state of rigid tension.
Right. Structural integrity moves from being a fixed state to being a dynamic, monitored condition.
Okay, now pivoting to air quality in those, deep urban canyons, places like Hong Kong, Lagos, Bogota, the source discusses these street canyon filtration masts.
This is a direct response to vehicular pollution that gets trapped deep within narrow city streets. These masts are slender, vertical devices designed to turn the streets into microventilation corridors, and they leverage the Venturi effect.
The Venturi effect, right? So for our listeners, that's the principle where if you force a fluid, in this case air, through a narrow or constricted area, its velocity increases and, crucially, its static pressure drops.
You've got it. The mast's geometry creates a constriction point, which effectively accelerates the air movement across the top of the device. This acceleration creates a low-pressure zone, which acts like a giant vacuum, actively pulling the stagnant, polluted air from the street canyon up and through internal chambers that contain these highly efficient nanocarbon filters.
So the city wind itself becomes the power source for a giant air purifier.
That's the idea.
But the device itself, a tall, slender structure, it must be subject to immense forces.
And that's where the key engineering challenge lies, defining the mast-to-sidewalk base anchorage. This thing has to perform two contradictory functions at the same time.
Okay.
Function 1. It has to resist extreme torsional wind loads. A tall, slender mast is inherently prone to twisting or dynamic oscillation in high winds. Function 2. It has to provide complete vibration isolation for the delicate filtration modules and the air quality sensors housed inside.
So the outside is being battered by the wind, but the internal mechanics can't feel any of that movement.
Exactly. If the filtration modules are subjected to that intense structural movement, they lose efficiency, their internal seals can fail, the sensitive instruments stop giving you accurate data. So the anchorage has to be a composite system.
What would that look like?
Maybe a base flange anchored deep into the slab, but then connected via a vibration-dampening puck system made of specialized polymers, or rubber, to the sensitive filtration housing. You have to hold it firm against the wind, yet mechanically decouple the internal components from that rigidity.
Fascinating. Let's get down to the molecular level for our last point in this section. Specialized material science, cryogenic concrete.
Right. Cryostorage concrete with integrated vapor barrier mineral matrices. This is coming out of Scandinavian research labs.
And this is for facilities storing materials at ultra-low temperatures where thermal integrity is absolutely non-negotiable.
Here, you're demanding that concrete act not just as a structural element, but as a flawless thermal and vapor armor. Standard concrete is porous. If you build a slab for a cryo storage area, warm, humid air vapor will naturally try to migrate through the microscopic pores towards the cold zone.
And once it hits the freezing point inside the concrete,
It freezes, expands, and creates microfreeze cracking. This is the dreaded freeze-thaw fatigue, but it's accelerated and highly localized.
so the solution is to change the concrete itself.
The solution is integrating these specialized mineral matrices, nanoparticulate additives that block or drastically slow down that vapor migration path. The material is engineered to be structurally dense and chemically inert against these vapor pressures.
But even with this advanced concrete, where's the subtle high-stakes failure risk still hiding?
It's always at the edges, at the transitions. The most critical engineering challenge is the slab edge detail. You have a massive temperature and humidity differential at the physical boundary between the cryo storage area and the adjacent warmer surface corridor. And that difference creates a severe vapor pressure gradient.
Can you even quantify that pressure? I mean, it's just humid air.
You can. In these deep cold environments, that osmotic push can equate to pressure differences that are measurable in hundreds of pascals. It's constantly pushing warm, humid air toward the cold, and this constant pressure differential can exert a lateral force at the slab edge.
A physical
A
force.
physical force that can destabilize adjacent non-structural partition tracks, the metal channels holding up the interior walls. The failure isn't the concrete cracking. The failure is the thermal envelope being compromised because the vapor pressure literally shoves the wall tracking out of alignment, creating gaps.
That's the ultimate architectural insight right there. Managing thermal vapor forces is a structural imperative, not just an HVAC problem. The concrete has to protect against an invisible molecular force trying to displace physical components.
We shift now from the physics of the atom to the politics of entire regions. The daily brief really signals that modern architectural practice has to engage directly with high-stakes policy, governance, and regional resilience. Architecture is stepping into the role of a spatial diplomat.
This transition is fascinating. We're going from designing systems that resist waves to designing spaces that facilitate political compromise. And the key document here is the request for proposals for the Pan-Midwest Agricultural Resilience and Policy Hub, RFP.
Right.
The scale is just immense. This is an institutional response to climate change, resource scarcity, and disaster management, and it spans 4 sovereign states in the heart of the U.S. Midwest.
And critically, it's not just a research center. It integrates highly charged political functions. You have hydrologic modeling and crop system innovation, yes, but you also have flood governance courts and dedicated water rights meeting rooms.
Wow.
And in the Midwest, water access and distribution are zero-sum political games. They're often decided through litigation and very intense negotiation.
So this is where architecture literally mediates political conflicts. The facility has to embody impartiality while providing the necessary infrastructure for contention and, hopefully, resolution.
And the suggested strategy for KING-KAMBUF in the brief emphasizes reframing the hub. They suggest positioning it not just as a building, but as a river basin diplomacy campus.
A diplomacy campus.
This transforms the building from just holding agricultural infrastructure into serving as climate policy architecture. The structure itself becomes an advocate for regional stability.
What does that strategic framing imply for the actual design of the campus? What does it look like?
It implies that every decision, from where you site it to the materials you use, has to convey shared ownership and neutrality. It can't look like it belongs primarily to State A or State B. The program itself has to be designed to promote genuine interaction. The brief notes the inclusion of structural labs for farm infrastructure resilience right alongside rural mobility design studios.
So you're forcing policymakers, engineers, and farmers into the same space.
Into proximity, yes.
Now, what is the core design challenge when you have 4 distinct sovereign states, each with competing, zero-sum interests in water usage and mobility rights, and you're forcing them to negotiate under a single roof?
The challenge is the definition of a neutral spatial strategy. The architecture must facilitate transparency for public engagement, but at the same time, it has to guarantee secure, confidential spaces for those high-stakes negotiations.
And if it's perceived as favoring one state's representatives?
The whole diplomatic effort could fail before the building even opens. If one delegation feels they have easier access to key modeling data or better sightlines in the negotiation rooms, that's it.
So the design has to manage traffic flows so no one feels disadvantaged. It has to manage the visual language so the space reads as mutually owned territory.
Yeah.
It's behavioral architecture applied to interstate governance.
It really is. And this complex political mandate leads directly into an abstraction exercise given as a portfolio prompt in the brief. The river basin negotiation.
The atrium.
A central atrium.
Yeah.
But the prompt demands that its geometry must visually express the dynamics of water allocation diplomacy.
You're talking about translating abstract concepts like flow, equity, thresholds, negotiation stages into physical form.
Yes. The brief explicitly mentions that the atrium must reflect concepts like levels, flows, cascades, and thresholds. And crucially, it sets a design constraint. No literal water features.
Oh, that's brilliant.
The metaphorical flow has to be communicated solely through form, light, and structure.
That constraint is,
Yeah.
it's genius. It forces the designer to abstract these complex social and political ideas into pure three-dimensional space. It removes the literal crutch of just putting in a fountain.
Think about how you'd abstract cascades and thresholds. A designer might use massive descending terraced ramps or monumental staircases. These would symbolize the flow of resources from upstream sources, the high levels, down to downstream recipients at the low levels.
And the threshold of an agreement.
That might be represented by a distinct change in material or lighting quality at the central lowest gathering point.
How might light be used here to symbolize diplomacy?
Light defines clarity, consensus. If the negotiations are contentious, the perimeter spaces, the private caucus rooms, they might be intentionally shadowed or cloistered, but the central atrium floor, where compromise is sought, that would be flooded with natural, clear light, symbolizing transparency and mutual visibility.
And the atrium has to accommodate both formal and informal functions. Formal negotiations need structured tables, defined boundaries. But the informal meetings, the hallway conversations that actually break deadlocks, they need fluid, chance encounter zones.
And the architecture must strategically curate those chance encounters. A designer might place coffee kiosks or shared material libraries on the transition points between the delegation's wings. The success of the atrium is judged not by its aesthetics, but by its capacity to lower the perceived political temperature and facilitate productive human interaction between rivals.
It's an exercise that proves the designer's primary material isn't concrete or steel. It's abstract, political, and social relationships.
Exactly.
Okay, we are now moving back from that grand political scale to the... Let's start with facade failure. Vertical micropressure delamination zones. What precisely is causing laminated panels to peel apart on tall buildings?
It's a critical and often overlooked consequence of the stack effect. In tall buildings, warm air naturally rises. This creates lower pressure at the bottom and significantly higher pressure at the top.
Okay.
And this effect is magnified in the facade cavity, that little space between the exterior cladding and the interior structure. That cavity traps the pressurized warm air.
So the facade cavity acts like a pressure cooker.
Essentially, yes. This trapped, pressurized air exerts an outward force, and this internal pressure can measure hundreds of pascals, often exceeding the negative pressure loads from external wind section.
So the pressure from inside is pushing out harder than the wind is pulling.
In certain conditions, yes. And this constant internal pressure causes localized stress concentration points, and over time, separates the layers of laminated glass or composite panels. Delamination. The deep lesson here is that facades must be designed with explicit controlled venting pathways to equalize this internal pressure. And the lamination process itself has to account for this constant outward stress, not just the lateral wind force.
It's the pressure differential between the atmosphere and the trapped air that's the killer. Okay, next, chemical heat plume uplift in specialized facilities like wastewater labs.
Right. Many industrial processes, particularly chemical mixing or biological digestion in labs, are highly exothermic. They generate sudden, intense bursts of heat. And this localized heat creates powerful, buoyant vertical air plumes.
Like a hot air balloon effect.
Exactly. And if these labs are constructed with suspended acoustic ceilings, those plumes can generate massive uplift forces.
We're talking about air currents acting like pistons, actively pushing up on the ceiling panels.
The required engineering modeling has to go way beyond basic ventilation calculations. You need computational fluid dynamics, CFD, to precisely map the geometry of that plume, the velocity and temperature profile, and predict where the maximum uplift pressure will hit the ceiling grid.
And the solution?
Heavily reinforced ceiling bracing, often anchored directly to the deck above, specifically designed to resist upward loading. And you pair that with thermal ventilation that immediately captures and redirects the hot air before the pressure can even accumulate.
A fascinating inversion of gravity where internal chemical processes are pushing components upward. Then there's this incredibly subtle failure mode. Artifact humidity buoyancy uplift under sealed museum floors.
This is a beautiful lesson in how thermodynamics relates to buoyancy. Beneath a sealed museum floor, especially one designed for climate control, you often have a crawl space or a highly conditioned plenum. If vapor migrates up from the substrate, from the foundation, into this space, that humid air is significantly less dense than the drier, temperature-controlled air above the floor slab.
The humid air is physically lighter, so it's creating a buoyant force underneath the floor.
Correct. This humidity gradient behaves exactly like a fluid load. It's exerting upward buoyancy pressure on the floor slab. And over time, especially if the slab is thin or weakly reinforced, this constant, invisible uplift can cause observable slab warping or distortion.
Wow.
So the deep lesson is that the vapor migration path has to be controlled meticulously. You use advanced vapor barriers beneath the slab to prevent this buoyancy effect from distorting the structural path. You're literally fighting the physics of relative air density.
Incredible. And finally, a key safety issue in containment environments. Pressure cascade hysteresis in multi-zone HVAC systems, like in public health labs.
In a biocontainment lab, air pressure is precisely controlled to ensure that air always flows from clean zones, which are high pressure, to dirty zones, which are low pressure. This pressure cascade ensures safety. Hysteresis describes the system's inherent lag. When the control system signals a pressure change, say, adjusting a damper, the physical airflow and the resulting pressure differential don't instantly match the signal.
It's like having brake lag on a really sophisticated system.
That's a great way to think about it. And during that lag time, the intended containment cascade can temporarily fail or even reverse, creating an unintended and potentially hazardous flow direction. Transient airflow, the movement during the adjustment, can be far more dangerous than a steady-state failure because it's so unpredictable.
So what's the takeaway for commissioning these buildings?
The commissioning process has to include rigorous testing of these hysteresis cycles. You have to ensure that the system recovers its intended pressure relationship quickly and predictably to minimize that risk window for biocontainment breaches.
Okay, let's pivot from invisible flows to dynamic forces loads caused by movement, asymmetry, or repetitive impact. We start with asymmetry in mixed-use structures. Differential service core torsion checks.
A service core, the part with elevators, stairwells, mechanical shafts, is typically the stiffest element in a tower. In mixed-use podium designs, the core is often pushed off-center for programmatic flexibility, which results in mass or stiffness asymmetry.
Okay.
So when lateral loads, like wind or a minor seismic event, hit this asymmetrical structure, they don't just push the building sideways. They introduce an immense torsional moment, a twisting force.
The building wants to wring itself out like a wet towel localized around that stiff core.
That's the effect. The deep lesson requires a rigorous analysis of the podium drift. Because the core is often centered in the tower portion, but off-center in the podium, the torsional pull concentrates precisely where the core ties back into the broader, less stiff podium slabs. Structural engineers have to ensure those connections are legible and robust enough to handle the twisting forces, which can lead to cracking and spalling if you only account for simple shear or bending.
Moving to industrial architecture, we have crane-pendulum drift echoes in fabrication bays. This sounds like structural choreography gone wrong.
It is a critical issue in manufacturing environments. Overhead gantry cranes carry immense heavy loads that swing rhythmically during transport. If the frequency of that repetitive swinging load, the pendulum motion, matches the natural resonant frequency of the primary steel frame, you get harmonic drift feedback.
The structure begins to amplify the swing with each repetition.
Exactly. This resonance causes the entire structure to sway incrementally more with each cycle. This leads to long-term fatigue in connections, failure of non-structural components like lighting rails, and eventually serviceability issues like differential settlement.
So how do you stop it?
The engineering solution requires detailed analysis of the frame's stiffness and the strategic integration of lateral dampers, which are tuned specifically to shift the structure's natural frequency away from the crane's operating frequency.
Now, let's consider the cumulative effect of small forces. Ballistic rebound microtorsion in long-span school gyms. This feels negligible, but the source stresses its importance.
This is a classic lightweight structural failure mechanism. In large, long-span gyms, the roof structures are often these lightweight steel joists. Repeated high-velocity impacts from basketballs or volleyballs hitting the upper walls or the joist connections. They don't cause immediate damage, but they exert tiny, high-frequency torsional forces at the point of impact.
So 1,000 tiny twists over a decade.
That's right. These microtorsional forces accumulate stress in the joist connections and along the purlins. And over years, these tiny repetitive distortions grow into serviceability issues. Ceiling tiles falling out, lighting tracks misaligning, internal partitions developing small stress cracks.
So the lesson is that even tiny, seemingly insignificant impact forces, when they're highly repetitive, have to be analyzed as cumulative fatigue loads in lightweight structure design.
You've got it.
And finally, a key safety load involving human behavior. Platform edge surge shear zones in transit hubs.
This is the critical recognition that human crowds are not merely static weight. When a busy train arrives, there's a collective, immediate wave of passengers moving forward to the platform edge. They're trying to gauge the best door access or get ready to disembark.
Right.
This concentrated dynamic shift of thousands of bodies creates an intense lateral pressure burst, a surge shear load right at the platform edge.
We have to calculate crowd behavior as a quantifiable shear load, separate from the static weight.
Structural engineers are now modeling this force in kilonewtons per meter of platform edge. The structure may be massive, but the dynamic, transient force of thousands of bodies shifting at once must be calculated. The failure mechanism is typically not catastrophic collapse, but localized failure of anchoring or connection elements, or excessive lateral movement that compromises the gap between the train and the platform.
Let's move on to sound. Sound is fundamentally invisible energy pressure waves that follow the path of least resistance. Architecture has to manage these vectors.
Precisely.
In courtrooms, where confidentiality is paramount, we see acoustic privacy transmission vectors. How does a private conversation leak out?
Voice energy often flanks the primary structural separations. A thick wall might be acoustically adequate, but if there's a continuous, hollow pathway, like a mechanical chase or a gap around ductwork, that sound energy will use it as a vector.
A highway for sound.
It's an internal highway, exactly.
Yeah.
In courtrooms, voice energy frequently travels along the internal volume of the HVAC ducts, bypassing standard insulation and leaking into adjacent confidential spaces like judges' chambers or jury deliberation rooms.
So the design lesson is clear. You have to trace the internal pathways of all mechanical systems.
And the solutions require integrating specific duct silencers, often internally lined with sound-absorbing materials, and designing dedicated insulated privacy corridors to physically interrupt and absorb the voice energy along these specific vectors before it can flank the primary structure.
How about the dynamic nature of sound? The brief mentions stacked unit acoustical drift in dormitories.
This points out that acoustics are not just static measurements of mass and thickness. Sound energy pathways can actually shift vertically based on the HVAC cycle timing. For example, when a fan coil unit in a lower unit kicks on, the increase in air velocity and the resulting pressure changes in the shared plenum can alter the sound conductivity of the air mass itself.
So the mechanical system doesn't just make noise, it changes how other noise travels.
Precisely. The mechanical system determines the dominant path of sound travel by changing pressure relationships and introducing new energy levels. A noise that was quiet when the HVAC was off might become clearly audible upstairs when the fan introduces turbulence and slightly pressurizes the shared floor-ceiling plenum.
So the design has to account for that dynamic state.
You have to insulate the pathways that open up during peak mechanical operation.
And finally, the structural implication of speech itself. Oratory-induced spatial resonance in large civic auditoriums.
This is the rarest but most interesting phenomenon. In extremely large auditoriums with specific geometric acoustic characteristics, the frequency range of a powerful human voice, especially a trained orator projecting loudly, can sometimes align perfectly with the building's own natural resonant modes.
Like pushing a swing at the perfect timing.
Exactly. The voice then acts as an unintended, self-amplifying structural driver, inducing actual measurable microvibration in elements like large ceiling panels or internal balconies. While it's typically not dangerous, the deep lesson is that speech has structural implications. The space has to be acoustically tuned during design to ensure its primary function, oratory, doesn't unintentionally compromise the structure's serviceability by aligning with its resonant frequency.
Our final cluster here addresses how chemistry and the environment actively degrade materials, starting with freeze-pulse slab memory in cold region transit platforms.
When concrete or asphalt in cold regions undergoes repeated freeze-thaw cycles, the water intrusion and expansion create microcracks. The source uses the vivid term slab memory because these microcracks aren't erased. They propagate and grow with each successive thermal stress cycle. The material retains a memory of its past temperature trauma.
So how does an engineer fight this cumulative memory?
It requires specific checking for freeze-thaw fatigue analysis, which is distinct from simple structural loading. Mitigation involves very specialized air entraining admixtures to create intentional microscopic air voids that accommodate the expanding water, and careful slab reinforcement patterns designed to distribute the thermal stress evenly across the matrix, preventing stress concentration points.
Next, a chemical failure point. Diurnal brine film shear loss on bridges. This is about de-icing salts.
Right. De-icing salt, or brine, forms a thin film on bridge decks. Combined with the daily temperature fluctuations, the diurnal cycles, this brine film actively reduces the deck's coefficient of friction. This shear loss means the bridge deck is temporarily but significantly more slippery than the design specifications assumed, which undermines vehicular control and traffic safety.
So material scientists need to account for surface chemistry as an active failure agent.
Absolutely. The chemical reaction between the brine, the asphalt, or concrete, and the temperature oscillations is a dynamic problem.
Mm.
The core insight is that materials are not passive. Their surface chemistry can actively undermine their design performance envelope.
And finally, an aerospace-related structural stress, jet shear glazing buckling analysis near airport aprons.
Near runways and taxiways, when large aircraft power up, the transient jetway creates these intense, high-velocity aerodynamic shear forces. These are not steady, static wind loads. They are rapid, extremely forceful pressure spikes that hit the building like a temporary massive hammer blow.
And this causes the glass to physically buckle.
Yes, momentarily. This requires specialized analysis of extremely fast, transient aerodynamic loading. Design solutions include significant mullion stiffening and specialized glazing assemblies that can absorb or deflect these high-frequency pressure spikes without yielding. Standard wind load analysis simply cannot capture the intensity or speed of a jet shear event.
Okay, so having established the theoretical physics, let's transition to where this advanced knowledge meets the reality of construction management and regulatory compliance. We're looking at specific failure scenarios and the mandated corrective workflows.
Right, the practical application.
First up, HVAC, duct inertia, and snapback. This scenario is perfect for demonstrating the consequence of mechanical start and stop physics. We have a convention center retrofit where long ducts are whipping slightly when the system abruptly starts or shuts down.
And the brief provides clear data points illustrating the scale of the issue. Duct length stretching up to 28 meters, pressure differential swings spiking between 1.8 and 2.6 inches of water gauge, causing a snapback displacement of 8 to 12 millimeters.
Which sounds small, but repeated thousands of times.
It leads directly to hanger fatigue and diffuser misalignment, a major serviceability failure.
So if you have a giant, long metal duct whipping back and forth, what is the professional 5-step mitigation workflow?
First, you have to model and map the inertia-induced bending regions along the duct runs to pinpoint where the maximum displacement is happening. Second, you add midpoint stabilizers. The critical element here is that these must use elastomeric bushings.
Okay, what do they do?
They don't hold the duct rigidly. They use the viscoelastic properties of rubber to absorb and dissipate the kinetic energy from the snapback, preventing it from transferring that whip motion to the hangers. They're energy absorbers, not just rigid connectors.
Makes sense.
Third, you have to rebalance the airflows to reduce the intensity of that pressure spike on startup. Fourth, you introduce soft start dampers, motorized dampers that gradually increase the airflow rather than slamming the pressure change instantly. This slows the kinetic energy generation.
And fifth.
The hangers have to be retensioned to the correct specification after all the stabilization is complete. The lesson is that mechanical start and stop physics must be treated as a structural dynamic load with long-term fatigue implications.
Next, a data center failure scenario. A cold region facility experienced heat chimney column bowing after a major retrofit to install high-density server stacks, a huge 15.7 megawatt heat load.
We established that heat is a structural load, and here's the proof. The vertical heat plume rise was measured at a terrifying 14 to 22 meters per minute, causing the steel columns to bow by 3 to 5 millimeters. The structural deformation was caused purely by internal thermal expansion gradients.
So the side of the column facing the hot air plume heats up, expands more than the cool side, and forces the column to bow away from the heat.
Exactly. And the mitigation workflow focuses entirely on treating airflow geometry as a structural load path.
What are the 5 steps to save the structure without turning off the servers?
First, you rigorously map the vertical heat plume geometry to identify the precise column exposure zones. Second, you install thermal baffles, vertical, non-structural sheets placed strategically, to redirect the intense heat plume away from the column flanges.
Get the heat off the steel.
Third, you apply heat-reflective composite wraps, often thin metallic foil or ceramics, around the high-exposure faces of the steel to reduce the rate of heat transfer. Fourth, you calibrate the server rack layout. This is vital, because you need to eliminate aligned updrafts that feed the chimney effect up the column line. And finally, you continuously monitor column deflection with sensors and adjust the airflow settings until the deflection returns to acceptable limits.
If the column moves, you adjust the air, not the structure. That's advanced performance engineering right there.
That's it.
Let's wrap up with 2 specific code insights that show how true compliance demands a nuanced understanding of spatial geometry and risk orientation. First, from the IBC, wind debris impact glazing zones.
Standard code often focuses on elevation and simple wind pressure. This insight stresses orientation logic. In regions prone to wind-borne debris hurricanes, tornadoes, the code mandates treating facade zones differently based on which direction they face.
Ah.
A side of a building facing a dense parking lot or a field of loose aggregate is at a high risk of impact, even if the static in-pressure calculation for that side is low.
So if that side is oriented toward the dominant storm track, the CUN demands impact-rated glazing, regardless of the calculation for wind speed alone.
Exactly. The takeaway is profound. Impact risk is directional. Code compliance is a spatial judgment call based on orientation logic and the surrounding terrain, not just a simple numerical check against elevation or generic pressure.
And finally, from the ADA, regarding operable parts reach with obstructed approach. We often remember the maximum dimension, the 24-inch maximum recess allowance for reach.
But the brief highlights that 24 inches is not a default. If an operable device, a thermostat, an emergency button, a light switch, is behind an obstruction like a counter or a guardrail, the obstruction's geometry fundamentally dictates the legal limit.
The device has to be reachable without the user leaning over the obstruction or requiring an excessive horizontal shift in posture.
Right. So if the counter projects far enough, the required reach distance is drastically reduced from 24 inches to perhaps 10 or 12 inches to maintain comfortable and safe accessibility. The obstruction classification changes the legal geometry entirely. The designer has to analyze the user's body interaction with the obstruction, recognizing that reachability is a spatial code built on human factors, not merely a dimension.
We have completed a comprehensive interrogation of the architectural insights with KING-KAMBUF brief. Today, you have gained insight into the full multidisciplinary profile required of the modern architectural leader, from engineering hydro-acoustics and cryoconcrete to leading four-state political planning initiatives and tuning structures against torsional stress caused by bouncing balls.
You now understand the hidden forces that drive tomorrow's most innovative structures. The ability to model and mitigate these invisible environmental, chemical, and behavioral loads, air pressure, thermal expansion, sound flanking, crowd shear, is what truly defines mastery in the AEC sector.
This deep dive has provided you with a shortcut to understanding the cutting edge of global architectural intelligence. The next time you walk into a complex building, you will see not just steel and glass, but a carefully engineered balance of forces, both visible and unseen.
And we'll leave you with the evening reflection from the mentorship brief. It's a question that connects the physical and the political mandates we discussed today, and something powerful to consider as you observe the infrastructure around you.
How can diplomacy, climate force, and infrastructure merge into a single architectural intelligence?